Example 6, write each expression as a single logarithm. We're still going to use the same properties of logs, and when you subtract, you can convert to division, and when you add, you can convert to multiplication. So it's definitely going to be a log base 4. They would all have to match, log base 4, log base 4, log base 4. But in the parentheses there, think of it as x divided by y times z, or probably a better way of writing that would be xz over y. X divided by y times z. Okay, so then the next one, part B, I see this subtraction again, which we're going to think of as division, but I also see this number in the front, which, if you recall, is coming from an exponent back here behind the variable. So we can condense it to a single log, log base b, and we know there's going to be a division in there. But on the top, the first number is r to the 4th, and on the bottom, the second number, s to the 5th. Now part C. Okay, so we can see these numbers that are going to get pulled over here to an exponent. And you see this addition is going to be multiplication, and this subtraction is going to be division. And so let's check it out. We're going to have a log base A of, and you're going to have x to the 1/3 times y to the 2/3 divided by xy. All right, now that's good, but that's not quite good enough because you've got this third root, and usually we don't write fractional exponents. So we can think of a third root like this. Okay, so take that third root out of there and you just have xy squared all over the xy. Example 7, assume that log base 10 of 7 equals 0.8451. What we're going to do is we're going to take a problem like log base 10 of 49, and we have to try to turn this 49 into a 7. And so the first thing that comes to my mind is if we said log base 10 of 7 squared. I like doing it that way because I could pull that 2 in the front using my properties. 2 times log base 10 of 7. But I know what log base 10 of 7 is. It is 0.8451. And so the problem becomes 2 times 0.8451, which is 1.6902. So I could have done it another way if I had called this log base 10 of 7 times 7, and using another property I would have said log base 10 of 7 plus log base 10 of 7, and so we would have used 0.8451 plus 0.8451, which would have given me the same answer. So you've got a couple of options there. It's just what you see fit. I kind of like the first way a little better. Part B says log base 10 of 70. So if you think about that, the first thing that comes to mind is log base 10 of 7 times 10, which is a little bit weird with that 10 because it's not a 7. But let's just use our properties and see what happens. You'd have log base 10 of 7 plus log base 10 of 10. Okay, so log base 10 of 7, that's our approximation there, 0.8451. But log base 10 of 10 is a special function. Log base 10 of 10 is equal to 1. Log base number of that same number is always going to equal 1. So we add those together and we get 1.8451. Lastly, we've got a theorem on inverses. We don't really have much to do with this right now. It's going to be really important in a later section. It's going to be how we solve more complicated equations, I guess. But the thing I noticed right here, log base a of a to the x is equal to x. So you don't really know what to do with it yet, but that's going to really help out when we're trying to solve equations.